All right. Okay. So we just finished up talking about really ice tables. And really, as I mentioned, ice tables are used to really solve for equilibrium concentrations in most cases. And it's when you're given initial concentrations and you want to try to figure out your equilibrium concentrations. So again, if we had, say, something like A plus B goes to AB, and the K was, say, 5. So let's say we had 0.1 molar A squared, or A2, plus 0.1 molar B2. What would be the equilibrium concentrations of all the species? So why don't you take a few minutes here, see what you come up with, see how we're doing. I'm just going to kind of erase and work towards the top of the screen so you can maybe see it. So we're going to do an ice table here. We could write our equilibrium expression as well. Get rid of this here, so put it over here maybe. So if we wrote our K expression for this reaction, it would be K is equal to AB. We would need to square it because of the coefficient, divided by our A2 and our B2. And in this case, this will equal 5 in this case. Initially, we had 0.1 molar of each of these guys. And again, it is safe to assume that you have nothing on the product side if they don't tell you anything about the product. Once again, because we have no products, we could probably again safely assume that the reaction is heading in that direction, which means we should expect the reactants to decrease. We should also expect our products to increase. So that really affects the change part. So this would be minus X. Again, the coefficient here is 1. This would be minus X for our coefficient is 1. And now on the product side, it would be plus 2X. Once again, the 2 there is important because it does take care of the mole-to-mole relationship. When we get to our equilibrium line, we're just going to basically bring everything down. So 0.1 minus X, 0.1 minus X, and 2X. Any questions on the table here? At this point, we're basically going to take our equilibrium line and our values, and we're going to basically insert it into our expression, which will give us something similar to what we saw previously, 2x squared divided by 0.1 minus x, 0.1 minus x, and that is going to equal 5 in this case. Once again, for our class, it's probably going to be something like this, a nice, even, perfect square on both sides. That would get us 2x divided by 0.1 minus x is equal to the square root there of 5, which will give us 2.236. Once again, we're going to multiply what's on the bottom to the other side. So when we multiply to the other side, we end up with 2x is equal to 0.2236 minus 2.236x. At this point, we're going to add the x to the other side to combine. And when we add it to the other side there, we will end up with 4.236x equals 0.2236. Lastly, here we're going to divide to the other side. And when we divide, we will end up with an x value of 0.052. I missed the 228. Try that again. Sort of like that number there, you know, if you missed a couple of numbers. Jesus. Try that here. Maybe there we go. All right. Take 2. There we go. So we have 0.0528, Once again, a reminder that when you do solve for X, it could end up being an equilibrium value, but it really is the change part of it. And it is all the X's that we see in our table at the equilibrium line. So it's all those X's that we want to put back into here. That means the concentration of A2 in this case will also equal B2. And that would be 0.1 minus 0.528. And we end up with 0.5. Type list a 0 there as well. You know, it's kind of right there. 0.1 minus 0.0. 0.0528. All right. 0.0472 molar, as it is a concentration. You would need that. And our AB here would equal, in this case, 2 times X would be 2 times 0.0528. Going to give us a 0.106 molar for that guy. Any questions on ice table or how to do an ice table here? Once again, if you take those equilibrium values and just got 0.106 squared divided by 0.0472 divided by 0.0472, you do get about 5. So again, a good way to kind of check yourself. Any questions on, yeah. How did I get 2 point, which one? 236? This guy? Yeah. Basically, we were back here. So basically, to kind of get everybody to the other side, we had to take everything that was on the bottom and we multiplied it to the other side. So we basically took 2.236 times 0.1, and then we basically took 2.236 times minus X, basically. So that's how we got there. Yeah. So basically, we multiply that entire bottom to the other side. And then factors in, right, to each of them. That's how we got the 2.236. And the 2.236 originally came from the square root of 5. If that's your other question. Yeah. So that's where it came from right there. Other questions? Okay. All right. So we're going to talk a little bit about a specific type of equilibrium constant, which is an equilibrium constant that is for things that are insoluble. And these are what are referred to as KSP. So KSP, the SP stands for the solubility product, right there. What the KSP is for. It is an equilibrium constant for things that are insoluble. So if you remember from like our solubility rules, there are certain things that when you put them together, you would expect a solid to form. And even though we sort of think of them as being insoluble, there is some degree of solubility that does occur with things that are technically even insoluble. So for example, if you take something, as we'll see, I think like silver chloride, based on solubility rules, when you put silver with chloride, you would get a solid that would form, as chloride is soluble in everything except for silver, lead, and mercury. But when you actually make this insoluble solid, it actually in solution is in equilibrium with its ions. So even though technically speaking, it is soluble, and technically speaking, you would expect a solid to form, even in solution, a little bit of it will break apart because they are basically in equilibrium with each other. So it sets up actually an equilibrium in solution, and KSP values are usually very, very small. So these guys are usually very, very small. And as we talked about, because the K value is very, very small, we mainly would expect to have reactants at equilibrium. And pretty much all KSP reactions are written like this: solid on the left, aqueous ions on the right. That means if we are really, really small values for KSP, it is pretty much going to be all reactants. But again, there is that like little small amount that will still be soluble and still break apart into ions. They're very small, like the example I gave earlier, like to the -36 and the -54, super small values. So for the most part, it's pretty much going to be insoluble, but it will still let off just a little bit of ions in solution. So the solubility product has only one value for a solid at a given temperature. So if we look at Bi2S3, it would break apart into these ions here. We'll write them a little bit higher here, as you can see. And we could write our equilibrium expression just like we normally would. We would take our products, which would be the Bi3 plus, and we would square it because of the coefficient, times the S2 minus, and we would cube it because of the coefficient. And once again, here, as we talked about earlier, we would not include our reactant because it's a solid. And this is what is known as a KSP expression. And pretty much most KSP expressions are just the products because all reactants are pretty much solid in these reactions. So it really is just products over really your solid reactants, which never get included in the expression. So for example, if a saturated solution of lead 2 chloride is prepared, if we take a look at lead 2 chloride, it will break apart into a lead ion with a +2 charge and a couple of chloride ions. The KSP would be our products divided by our reactants, but once again, this is a solid, so it would not be included in it. So because it's a solid, it's not going to be included. In this particular case, is prepared by dissolving distilled water, and the lead concentration is determined to be 1.6 times 10 to the -2. So we actually could use an ice table to help us figure out what the KSP value is. So for example, if we did our ice table here, so initially here we have nothing of our products. The change here would actually be plus S plus 2S, Rx, and E would be S and 2S. Now, the reason I use S is because I'm familiar with it, and usually in these problems, we use S. We use S instead of X, and that is because S stands for the molar solubility. But if you want to use X, you can use X too. It doesn't really matter which letter you use there when you do it. So if you want to use X here, you can use X by all means. And what this tells us is we already know that from the problem, the lead 2 is 1.6 times 10 to the -2. So that would be our X value. So we can basically take 2 times that. So we know from the problem that lead is 1.6 times 10 to the -2. We know that the chloride would be 2 times X. So 2 times 1.6 times 10 to the -2. And we still need to square it in this case. So if we do all that good stuff, we should end up with a KSP like we see there on the bottom. We take our 2 times 1.6 to the -2. We'll square it and times it by 1.6 to the -2, giving us 1.6 times 10 to the -5. So in this case, because they told us what the equilibrium concentration of lead was, we could use our ice table to sort of work backwards to figure out what X is, and that will allow us to figure out our KSP value. Any questions on that there? Yeah. Yeah, so in this case, let's see here if I can get backwards here. Find somewhere I could write, maybe. There you go. So in this particular case, it was this, right? So in solution, basically what you would have is a bunch of solid of PbCl2, basically mostly, but you would have a little bit of lead and chloride that will kind of float around. So initially, because salt is not included in the equilibrium, we don't worry about this side. And that means that what's going to really happen is just a little bit of it is going to break apart, which means we originally started with 0. So what's going to happen is some of this solid is going to break apart into those ions. So we're actually going to gain some of those ions as a result of that. We would technically move minus X on this side, but we don't need to because it's a solid, it won't be included in the calculation. So that's why technically we are losing a little bit of this, but we don't have to actually worry about it for the calculation part because it's a solid. Now, if you had something that was aqueous on that side, which you wouldn't in this type of problem, you would obviously still do the minus on that side and the plus on the other side. Other questions on that? And again, we were able to sort of work our way backwards because they basically told us the concentration here of lead 2 in the problem. And obviously, as we can see from the table, that equals X, which is what gives us this value. And those are really all the values that we need to basically put it into our expression of this guy here. Other questions on that there? We did that guy. So we want to calculate the solubility of silver chloride in water. So just to run through the calculation here, silver chloride would be our solid based on solubility rules. It would break apart into a silver ion and a chloride ion. And in this case, they did give us the KSP, which if we took our products would be our silver ion times our chloride ion, and it would equal 1.6 times 10 to the minus 10, which was obviously given to us. So in this case, when we really aren't given any numbers, we could do these type of problems by just assuming zeros to start with. So once again, we would have 0 for our silver and 0 for our chloride. Here in this KSP, because this guy is a solid, we're not going to worry about any of those initial guys where we normally would have a number or something like that. The change part here, again, we're not going to worry about this guy because it's a solid. That normally will still be our negative side. Our positive side would be over here, plus X, plus X. That means at equilibrium, again, not going to worry about this guy. Going to give us basically our X's and our X's in this case. Just like before, we're going to then take our equilibrium guys and put it into our expression. And if we do that, the KSP will then equal X times X, which is 1.6 times 10 to the minus 10. That is X squared is equal to 1.6 times 10 to the minus 10. That is a square root of both sides on that case, giving us an X is equal to 1.3 times 10 to the minus 5 in this case. In this particular case, if I wanted the concentration of the silver ion at equilibrium, it would be 1.3 times 10 to the minus 5 molar because it equals X. If I wanted the concentration of Cl minus at equilibrium, it would also be equal to X, which would be 1.3 times 10 to the minus 5 molar. And now the part that you can sort of follow along here with is this. If we wanted to really know the concentration of the whole entire thing, which is this guy here, we could just use stoichiometry. Say from our silver, it is a 1-to-1 relationship between silver and the whole thing, which means the concentration of silver chloride at equilibrium would also equal 1.3 times 10 to the minus 5 molar. You could do it with the chloride. It is a 1-to-1 between the chloride and the silver chloride. So you will get the same concentration. So the concentration works both ways. In this case, this is the concentration of each of these things at equilibrium. That is really the moles per liter. That is what is referred to as the molar solubility. It is basically how many moles per liter of that solution you can, or substance you can get to dissolve. And again, it is also sometimes when you do take 1B, sometimes referred to as S, or the molar solubility is what is sometimes referred to as that. Question on that there. All right, so that was our preview of ice tables. You'll see it again in 1B. Other questions on that? All right, that wraps up all the official lecturing here for our class. All right. What we're going to do now, I think, is for a few minutes or so, I think we'll start heading through some of the earlier chapters, kind of reviewing for the final. We'll stop. We'll talk about the exam that's coming up. We'll talk about checking out a lab and really what's left here of our class for the semester. But we'll use a little bit of our time here, maybe 20 minutes or so, and we'll start talking about some of the earlier chapters, and we'll continue probably reviewing for the remainder of our lectures that we have left. We have one before the exam on Wednesday, and then obviously on Monday, which is our very last day, we'll continue kind of reviewing. So just give me a second to get some pages here to write on. The final is comprehensive over all the chapters, so we might as well just start way back when, chapter 2-ish, I think, here. So a little review action here for the final. All right, so chapter 2 was really the first chapter where we talked a lot about really measurements. So remember that when we do take measurements, no matter what type of measurement we take, there's always some degree of uncertainty associated with the measurement. So as we saw, if we had something like, if this was a ruler and these were centimeters and we were measuring like this arrow here, what we always want to do when we do take a measurement is to look at the scale. And in this case, our big markings here are 1 centimeter. We have 10 markings in between, which means each of the smaller markings is 0.1 centimeters. So obviously this got to be 1.1, 1.2, 1.3, 1.4, 1.5, 1.6. Now remember that when you do take a measurement, there's always some numbers that everybody should agree upon. So everybody looking at this should agree it is at least 1.5. But then it's not obviously exactly at 1.5 like we talked about. It is maybe a little bit between those two numbers. So some people may think it's exactly in half. Other people may think it's a little less than half, a little bit more than half. And that's really where the estimation comes into play. So for example, I may say that it is 0.55 centimeters. And when you do record a measurement, there's always several things that's really important. You always want to record all the certain numbers plus that first uncertain number. And that really is what are referred to as significant figures, right? So obviously in this particular measurement, there are 3 significant figures where the uncertainty lies in the last significant figure that is written. Remember that it is the last significant figure that is written, not always the last number written is the uncertain number or the estimated number, but it is the last significant figure that is written. The other really important thing is you should always include units, right, when you take a measurement. When you do read it, right, you want to look at the scales because they can change. As we talked about, you could have 10 and 20, say milliliters, and we were somewhere in here. And in this case, there's actually only 5 markings between 10 and 20, where our big markings would be 10 milliliters. Each of the small markings in this case actually would be 2 milliliters. So that would be 12, 14, 16. So obviously our meniscus here is between 14 and 16, which means the best you could do on something like that would be 15 milliliters, where the uncertain number actually would be the 5 in this case, and it would have 2 significant figures. Questions on that there? Remember that we do count significant figures, right? And all non-zeros are significant. When we come to zeros, there are a few different types of zeros. There are leading zeros, which are not significant. And that would be something like this. All these zeros here are not significant. Remember, you do not start counting until you hit the very first non-zero number. So this guy would have 3 significant figures. There are trapped zeros, which are significant. And those are like 4004. All those guys are significant. You would start counting significant figures at the first 4. Those zeros in between would be significant, and the 4 at the end would be significant. So this guy would have 5 significant figures here, as they all would be significant. And then we have these zeros at the end, are trailing zeros, and they may or may not be significant. What determines if they are significant, right, is whether or not there is a decimal point in the number. So if there is a decimal point, then the number would be significant. And remember that the decimal point does not need to be right next to the number or anything like that, or the zeros, but just needs to be anywhere in the number. Obviously, if there is no decimal point in the number, then it is not significant. So if you had 12,000, like so, this would be significant. Then all these zeros would be significant as there is a decimal point right there. This would be 3, 4, 5, 6 significant figures. If I wrote 12,000 like so, this would have only 2 significant figures, as these 2 would be significant. The zeros here would not be significant as there's no decimal place. This also is what we were just talking about in terms of the uncertain number and the top measurement. The 0 here is the uncertain number. And the bottom one, it is actually the 2. That is the uncertain number in that bottom one. So again, it's not always the last number is the uncertain number. A lot of times it is, but it really is the last significant figure that is the uncertain one. We also talked about significant figures in calculations, and a reminder that if you multiply or divide, your answer should have the same number of significant figures as the number with the least number of sig figs. So if you took 4.53 times 2.0, this has 3 significant figures. This one has 2. Your answer should end up with 2 significant figures based off of the 2.0. And that is different than when we add and subtract. When we add and subtract, we look at the number of decimal places. And it is the number with the least number of decimal places. So if we took 4.32 plus 1.2, add them together, 255. This number here has 2 decimal places. Next number has 1 decimal place. So we would go to only one decimal place here and round to 5.5. 5.5 has one decimal place, but it has two significant figures if you needed to carry that on with some type of calculation. Any questions on that there? As we've gone through this semester, we've talked about the importance of scientific notation, and more important, making sure that you hopefully still remember where your buttons are on your calculator. Remember that proper scientific notation is a number times 10 to the n. This needs to be a number between 1 and 10. That is also a positive or negative number, depending on which way you move the decimal place to get a number between 1 and 10. In terms of significant figures, all the numbers before the times 10 part are always significant. So scientific notation is a way that if you need to give an answer to a proper number of significant figures, you could actually just write in scientific notation, and you could really control how many significant figures that you put in that answer. And again, as we talked about, make sure that you always use your exponent button. And remember that when you do use these buttons, they really represent the times 10 part of the number, which means you do not need to hit the multiplication button or anything like that when you punch them into your calculator and you go through it. We talked about conversions and dimensional analysis in this chapter. Remember, this is the big one we talked about the whole semester. That's how they want you to really set up things as you go through chemistry here at Saddleback. They want you to really show everything that you can in dimensional analysis, which is a way that we use conversion factors and units to show things canceling out. Remember, from any equality like 12 inches equals 1 foot, this is what's referred to as an equality. You could write two conversion factors like 12 inches over 1 foot or 1 foot over 12 inches. And we use these to do problems. So if we had 525 inches and we want to know how many feet that was, we would write it something like this, 525 inches. Remember, opposites attract. So although it's not written as a fraction, those inches are up on top, which means to get rid of them, we need to go opposite. So 1 foot is 12 inches. The inches will cancel. And in this case here, we got 525 divided by 12. Gets us 43.75 feet. Now, in terms of significant figures, remember that this, which is a conversion factor, is considered an exact number. And if you remember, exact numbers are things that are basically one of two things. Either they are definitions, like 12 inches is equal to a foot, or they are something that is counted, like I got 5 apples on the desk or something like that. So because they're an exact number, they technically could have as many significant figures as you want. So what that means is typically in calculations, we ignore them in terms of significant figures. So that means in this case, we would actually look towards this number, since we're multiplying and dividing here, which has 3 significant figures. That means that we should end up there. And we also should round up because of the 5 that's next to it. So we should end up with 43.8 feet would be our correct answer in this case. Any questions on that there? If you have multiple conversions to do, you could just continue on, obviously, with the dimensional analysis setup. That's their preferred way of how you do it, all in one big calculation. If you do want to break it up, as we talked about, it's really important not to round, right, until you kind of get to the very end, but you should keep track of your sig figs and all that good stuff as you go along. Remember that in terms of conversion factors or qualities, if it is a English to English conversion, you're good. If it is like a metric to metric conversion, you're pretty good. You don't have to really worry about significant figures. But really, if you do kind of cross over from metric to English, or obviously the either way where you're going on that, you really should look at the value of the conversion factor in terms of determining significant figures. A couple of exceptions, like 1 inch is exactly 2.54 centimeters. That one you don't have to look at. You know, if you didn't use maybe the exact number for grams, like 454 grams equals 1 pound. These are different units. Grams are metric, pounds are English units. You would look at the number, not the one that's a 1. So always in a sort of metric to English conversion, there's always going to be one guy that's 1, and then the other guy will have an actual number. So if you do need to look at the metric to English conversion factor, you would always look at the number part, and obviously the one that's the 1 you would ignore as an exact number. Any questions on that there? Now, we also talked about density there in that chapter, I think, as well. Density, right, is mass divided by volume, and common units of density for solids and liquids typically have grams per milliliter or grams per cubic centimeter. Remember that a milliliter and a cubic centimeter are basically the same thing. They both are volumes. A milliliter is typically obtained by just taking a volume measurement, while a cubic centimeter is something like we did in the first couple experiments where you measured length times width times height. Again, you could do length times width times height, all in centimeters times centimeters times centimeters. That gives you a volume. So 1 unit of centimeter by itself is a unit of length. But if you have kind of length cubed, that is a volume that you're looking at. For gases, which we got a little bit into, I think, but not too much, the units for density are a little bit different. It's typically grams per liter is typically the units that you see if you calculate the density of a gas. Remember that there is a formula for density, which is M divided by V. That means V is equal to M over D. And we could also solve for M, which would be V times D in this case. And you could do your DMV triangle we talked about to help you remember that. So this is obviously a formula that you do need to know. And obviously, if something is more dense than water, it will sink. Something is less dense than water, it will float. Obviously, if we have some liquids that are different densities, we will get them to kind of layer out from one another, where the sort of higher density is on the bottom, the lower density is obviously up on top. There are a couple ways that we can sort of get volume in a density sort of calculation. One is to do the length times the width times the height and get cubic centimeters. One is to simply fill up a container and take an actual volume reading, which would give us milliliters. And a very common sort of way that we do get volume in a density calculation is we do what is referred to as volume by displacement. And that is where you basically fill up a container with a liquid to an initial volume. You can take something that is solid basically and drop it in. The result of that is the solid will raise the volume to a final volume. And really, if you take the difference between where it initially started and the final volume in that container, that will give you the volume of the solid object, would be our final volume minus our initial volume. So that is a very, very common way that we get the volume of a substance there. Any questions on that there? That I think is chapter 2. We then kind of rolled, I think, into chapter 3, I think. Chapter 3 wasn't a super long chapter. We talked about different phases of substances, solid, liquid, and gas, and going obviously backwards from each of these. Remember that as you go from solid to liquid, that is what is known as melting. As you go from liquid back to solid, that is freezing. Both of these occur at the same temperature, and that is the normal melting point or freezing point of a substance. As you go from liquid to gas, that is evaporation or vaporization. As you go from gas back to liquid, that is what is known as condensation. Also, these guys occur at the same temperature, and that is the normal boiling point of a substance. You also could go directly from solid to gas, skipping the liquid phase, and that is what is known as sublimation. And going back from gas to solid, skipping the liquid phase, deposition. We talked about these phase changes in terms of energy, going from solid to liquid to gas. Those are all endothermic processes where you have to put heat and energy in to do so. It has to be absorbed. Going from gas to liquid to solid, those are all processes where energy is released, and that is an exothermic process where we release the energy. We also talked, I think, in that chapter there about physical and chemical changes. A physical change is basically what you start with and end with are fundamentally the same thing. And that's different than a chemical change, where what you start with and end with are two fundamentally different things. Usually a chemical change is a chemical reaction that takes place. It's usually when we have that occur. Remember that that you can not get back in a chemical change your original components by any type of physical means, but typically in a physical change you can't get it back. Obviously, a change of state is a common physical change. A change of state, when something goes from solid to liquid to gas, all they are doing is just changing their state. They are still fundamentally whatever they are, like the ice cube. As it melts from a solid ice to liquid water to steam, they're all water, so they're all the same. Chemical change, you know, something like the formation of rust, iron and oxygen come together, and they basically bond together. We also talked about atoms, which are the basic blocks of matter, all made up of protons, electrons, and neutrons. We have molecules, which are a combination of two or more atoms, like I2, Cl2, H2O. We also have compounds, which are a combination of two or more atoms from different elements. Like H2O, CO2, whatever it may be. A reminder that I2 and Cl2, they are not compounds, they are molecules, and they're also elements, right? So elements are really the basics of what everything is built off of. The basic representation of elements are atoms, and you can't go any further back than elements. So you can break things back down from compounds into elements, but you can't go any further than that. We also talked about a substance, a pure substance. So something like water by itself, something like sodium chloride by itself. These are all pure substances. And those are not to be confused with mixtures, which is a combination of two or more pure substances together. Where they retain their identity. So even though it may look like everything mixed together, something disappeared, something went away, when you do make a mixture, it is only a physical change. It is not a chemical change. And a pretty simple example of that is basically taking these two guys together. We take these two pure substances together and we mix them together, we get a mixture of sodium chloride solution. And in a sodium chloride solution, what is really happening is we have our sodium ions, we have our chloride ions, and we have our water molecules basically surrounding each of these. There's just a lot of water molecules. So to our naked eye, it appears the sodium chloride has gone away, but it really hasn't. It's just pretty much gone into a lot of waters in their way. Water can do this because, as we talked about in a previous chapter, water is polar, right? There is a negative side to water, which is the oxygen side, which is why it's attracted to the positive ion, and the hydrogen side, which is the positive side of water, which is why it's attracted to chloride. So when you take something like sodium chloride and you dissolve it in each other, the salt basically gets mixed into all the waters and basically they disappear or dissolve. We know that they are both there and still there because we could simply heat this thing back up. And as we would heat this up, all of our water molecules would evaporate. That would allow these two ions to come back together to make our solid sodium chloride. The water could also be trapped if you wanted to, and you could get back to liquid water. But in our cases here, we just kind of let it go off into the environment. That led us to sort of two types of mixtures. One is a homogeneous mixture. Where everything looks the same throughout. So everything mixes really well. Everything looks the same. And a heterogeneous mixture where you see different layers or phases. They really don't mix very, very well. But regardless of whichever type of mixture it is, homogeneous or heterogeneous, you could do some type of physical aspect to it to get back the original substances. We talked about filtration, which we've done a number of times throughout the semester. In a filtration, right, we take like a funnel with some filter paper. And it's a good way to separate out a solid from a liquid, where obviously if you poured that into there, the solid would stay on the filter paper, the liquid would go through. Hopefully you have a container to catch it in. And again, that's a very simple way that you can separate out those two things, like a heterogeneous mixture. A homogeneous mixture, you could do something like distillation. And that was when you kind of had this closed environment, if you remember, and maybe you had something like salt water on one side. You got this kind of tube that connects both sides that's really cold. So as you heat something like the salt water, the water starts to evaporate, but it has nowhere to go. So it goes through this cold tube and through condensation, and you get your liquid. As you continue to heat the salt water, you basically will evaporate all the water to the other side, and you'll be left with just the salt on the left-hand side. When it's all said and done, you'll just have this solid salt. And again, you're able to separate out both parts of the mixture in their original components. So again, homogeneous or heterogeneous mixtures, you could always separate them out and there should be no issues. Any questions on any of that stuff there from